All right, let's get started. So today, we will finish this local features, and then we'll do a lab regarding regarding image stitching. Okay, so last week we talked about what did we talk about last week? What did we talk about last week? Blob detection or corner detection. So we want to do blob detection. Because that's how SIFT detector is applied for, is used for. But we started from Harris corner detection. Okay, so how to do corner detection? Well, to do corner detection, we look at, we examine the gradients or derivatives within a window. So that's how we do corner detection. We examine the changes. We examine the changes in image content if we move the window towards some direction. And such changes are characterized. Such changes are characterized by the x derivatives and y derivative within this window. So such changes are characterized by the second moment matrix M, which is a 2x2 matrix, and each element is computed using either x derivative and y derivative with respect to every single pixel within the window. Okay, and we have summarized the property. We have identified some interesting property of Harris corner detection. So as reflected in their results. So what can you observe in the results? You can observe the detector. The detector is robust to variations in rotations, because even though the object is rotated by some angle, it can still successfully identify the same corner pixels. Okay. However, well, of course, it's not robust to viewpoint change. I mean, like this. It's not, because the image content has been changed, because you take the image from different views, and so you don't see this part if you view the image from this angle. Okay, so of course, it cannot be, it's not robust to, it's only robust to viewpoint change such as rotation. Okay, it doesn't, it's not robust to viewpoint change if you take the image from its back or from the side. Okay, and we have summarized that the Harris corner detection, it has a major limitation. What is that limitation? It's invariant to rotation, but it's not invariant to scales, meaning that it cannot identify corners of different scales. And this is understandable because when we do Harris corner detection, we only apply a fixed window size. We only apply a fixed window size such as this. Therefore, such window size can only identify corners of certain size. If you apply such a small window to identify a big corner, then you won't succeed because due to the large scale of the corner, the window will look too small compared to the size of the corner. Well, simply put, if you move the window slightly along the if you move the window along the edge of the corner, if you move it this way or this way, okay, it will be the edge of the corner will look as edges to this window. Okay, so you can imagine if you move this window up and down, okay, just slightly up and slightly down, you will identify this pixel as an edge pixel. Okay, and similarly, if you place the window here and move it slightly to the right or slightly to the left, it will still identify this part as an edge pixel. And similarly, in this case, simply because the window size is too small compared to the size of the corner, so it cannot encompass, it cannot contain necessary gradient information. Okay, it can only encompass this area. It cannot contain the necessary gradient information to identify such a corner. So the solution is to use windows of varying sizes and calculate. Hopefully we can applying such a series of window of varying size, and then we calculate a score for each window. We calculate a score for each window, calculate a response function for each window. And the highest, the scale, the window that gives the highest response could be the purple scale for the corner size. Okay, because we do not know the size of the corner. Because we do not know the size of the corner. We do not know whether this is a big corner or a small corner. So since we do not have such a prior knowledge, we just apply a series of window, a set of window of varying sizes. Okay, and the window that gives the maximum response could be the purple window for the current corner, for the corner at the hand. Okay, so that's how we do automatic scale selection. We want to design a proper function and such function can give us and such function can gives the highest response when the window size is appropriate. When the window size align best with the corner size. Okay, so it all depends on how the design and selection of such a proper response function. Okay, suppose we have such a magical response function, and you will give maximum response when the window size is the right size for the corner. In blob detection, such a response function is called Laplacian of Gaussian. Well, so this, I put a few slides here for your references about the first order derivative, second order derivatives. Okay, so second order derivatives is measure the changes in first order derivatives. Okay, well, it measures the curvature of the original function. Well, these are for your reference only. For example, the Gaussian function. This is the Gaussian function. This is the first order derivative of the Gaussian function and the second order derivative for the Gaussian function. You may notice the second order derivative of Gaussian function. What does it look like? It looks like very much as this. The second order derivatives of Gaussian. This is the Laplacian of Gaussian function. Looks very much like this. Okay, so previously we mentioned we need a proper response function, and the Laplacian of Gaussian happens to be a suitable response function. Well, let's explain this. Suppose we have an image like this, and there is a black blob with a bright background, white background. Okay, and the blob size is r, meaning that the radius of the circle is r. The radius of the circle is r. Well, the maximum response, if we apply the Laplacian function, this is the Laplacian function. And you can see there's one parameter. There's one parameter in the Laplacian of Gaussian. And that parameter is sigma. Okay, so the sigma parameter is also the parameter in the Gaussian function. But here, the Gaussian function is one-dimensional. It's one-dimensional. But since images are 2D, so we will consider gxy, which has two parameters. Okay, so the gxy Gaussian function should be right. gxy Gaussian function. So in Gaussian function, the parameter is sigma. Okay, so the Laplacian of Gaussian function is given. Well, you don't need to know Well, if you're interested, you can derive the Laplacian of Gaussian. If you're interested. But let's just assume the Laplacian of Gaussian can be written in this form. So we are given a Gaussian. We're given a Gaussian function, right? Gxy, because it's a two-dimensional function, Gxy. Okay, and let's take the second order derivatives with respect to x, and the second order derivative with respect to y, and then we can derive this, the Laplacian of Gaussian. So the Laplacian of Gaussian function also have this sigma parameter. It also has this sigma parameter, of course, because it's from the Gaussian function. Okay. So so different sigma will gives different log. Let's call Laplacian of Gaussian log. Okay, so different sigma will result in different log. And this is one log with respect to certain sigma. If you increase the sigma, you will get a different log filter. And similarly, if you decrease sigma, you will get also another different log filter, right? So the idea is that suppose we have sigma 1, sigma 2, sigma 3, sigma 4. Okay, suppose we have 4 different sigma. And we apply the 4 filters. We apply 4 filters on this image. The maximum response. Which filter will give maximum response? Only the filter with sigma equal to this number will give maximum response. Okay, so only when the sigma value is equal to this. Only when the zeros of the Laplacian align with the circle. So this is R. This is R. Okay, so only when sigma equal to this. Well, now suppose our sigma 1 is equal to and sigma 2 is equal to this. And sigma 3 is equal to 2R. And sigma 4 is equal to 3R. Okay? Then neither this will not give maximum response, and neither will this, and neither will this. So only sigma 2 will give largest response because its sigma is equal to this R divided by the square root of 2. Okay, so only when the size of the filter is appropriate, only when the size of the filter match with the size of the blob, it will give the maximum response. Clear? So that's the idea. Okay, so the idea is like we apply many Gaussian filters, and these Gaussian filters have many log filters, and these filters, they have different sizes. Okay, and the sizes that best match the filter with the filter size. When the filter size best matches the blob size, then that filter will achieve the maximum response. Okay, so that's the idea behind LOG. Okay, well, we have an image. Now we have an image. And if we apply LOG with sigma equal to 2, and this is a small filter. This is a small filter because sigma is small. Okay, then it's like we apply this LOG filter, you know, the LOG filter. We scan the image with the LOG filter. We slide the filter across the image. Okay, across the image. And you will see the white pixel indicate maximum response. So you will observe white pixel here, the brightest pixel at this position and this position. And also the darkest pixel here and here. Well, let's. So the maxima achieves at where? The maxima achieves, can see, achieves at the eye region, because the eye is a black blob. And also here, there's a black blob here. So the sigma, this one, this is a small filter. And also the minima is also achieved. You can see there's a white blob here and another white blob here. Also here. See? So the LOG filter, you will give maximum response for the black blob, small blobs, and you will give minimum response for the white blobs. Well, things are different if we apply. Well, this is the input image. Input image, you can see this is the head region. The head region. Okay, the head region here. And this is the resulting when we apply LOG with sigma 2. If we apply LOG with sigma 2, if we scan the image, apply the filter across the image, and we will achieve maximum response at this place. So this pixel gives maximum response. Well, you may observe, well, this area and this area. So you can see this pixel happens to be the center of the eye. Okay, this one, the pixel that has highest response, maxima, happens to be the center of the eye region, because the eye is just a black blob. Okay, so here, this is the highest response, the center of the black blob, center of the eye region achieves the highest response. Okay, so if you apply sigma 2 filter, sigma equal to 2, sigma 2 LOG filter, the highest response is achieved at the center of the eye. The center of the eye, because the eye itself is a small, dark blob. However, if you apply a large LOG filter, you can see the maximum response is achieved at the center of the head region. The head region. If you apply sigma equal to 10, then the head is a blob. The highest response is achieved at the head region, because the head is can be roughly seen as the as a blob. Well, sigma equal to 10, I think this will be bigger. Okay, the circle might be bigger. Anyway, it just demonstrates that if you apply log filter of different sizes, then you will identify blobs of different scales. Okay, so applying this filter leads to the highest response around the head region, Okay, well, this is we have explained this. This is the input image, and this is the head region. The head region. Okay. Now we convolve this image with the log filter. See, this is our log filter. The log filter, remember it has a shape like this. The log filter. So the center of the log filter is the darkest because it has the smallest value. If we convolve this image with log, and this is our results. And you can see the highest response. The highest response is achieved at the eye center, the center of the eye. And you can observe the center, this eye region, the size of the eye, it may match the size of the log when sigma is 2. Okay, when the filter size match the blob size, it will give highest response. Okay, so log, intuitively, log looks a bit like an eye. And it responds maximally in the eye region because the size of the eye region happens to align well with the size of the log filter when the sigma being 2. Their sizes match with each other. That's why it achieves maximum response. Okay? This is another example. So say we have blobs of different sizes, right? Blobs of different sizes. How can we simultaneously identify all these blobs? You cannot use one type of filter. You have to apply a set of filters with varying sizes because different filter is specialized in identifying a certain scale of blobs of a certain scale. For example, this filter match these blobs. Therefore, it will give the highest response among all these filters for this blob. Okay. For this blob, this filter will give the highest response among the 4 filters. This one will give the highest response for the small blobs. And similarly, this filter will give the highest response for this blob among the 4 of them, among the 4 different filters. And this one will give highest response for the large blob. Okay. So in order to identify blobs of varying sizes, you need to apply filters of varying sizes simultaneously. Okay, now let's take a look at our sunflower image. Within this image, you can see there are many sunflowers with those near the camera has larger size, and those further away from the camera has smaller sizes. Okay, we have explained that because when we take the image, when the image is taken, it follows the perspective projection, and objects near the camera will have larger image size, and those further away from the camera will have smaller image size. Okay. How can we identify all those blobs simultaneously? We apply filters of varying sizes. So notice that in order for comparison, we cut the image, we cut the original image to its 3/4. So we reduce the size of the original image a little bit. And then we apply filters. So this is sigma 2. This is a small filter. Remember previously we apply log with sigma being 2, and this is 2.1. So their sizes are similar. And you can see if we apply such small filters, what type of blobs will give maximum response? Let's take a look at the original image. You can see those sunflowers further away from the camera. These sunflowers will give maximum response because their sizes match the size of the filter. And the top one is the scale down the image. So remember we have scaled down the image a little bit, and we apply the same filter. We apply the same filter, and because the image is scaled down, while the filter size is still 2.1, sigma being 2.1. So the maximum response achieved at the top image should be different from those from the original image, right? Because the top image is smaller. The top image is smaller compared to the original image. Okay, and if you apply the same filter, their responses are different. Does it make sense? Because the top image is smaller than the bottom image. If you apply the same filter, well, the filter has the same size filter. If you apply the same filter across the image, okay? If you apply the same filter across the image, they will give different responses, right? Because the top image is scaled down. The top image is scaled down. So the size of this blob, is different with the size of this blob. That's the sunflower, but they have different sizes now, right? So the size of this blob is different than this one. Okay, so the same filter will give different response. Okay, now we apply the same filter onto the two images, and then we enlarge the scale down image, and you can see their responses are different. Get that? Can you get that? We apply the same filter over the top image and the bottom image because the top image is scaled down. It's scaled down. The sunflowers, the sizes of the sunflowers in the top image are different from those in the bottom image. Therefore, when you apply the same filter, it will give different responses. Okay, and you can see the maximum responses are achieved for the sunflowers that they are closer to the camera than this. Okay, because the images are scaled down. And similarly, when we apply a slightly larger filter, well, you can see now the maximum response are achieved for sunflowers closer to the camera. Okay, at such distance, closer to the camera. And for the scaled down image, well, these are maximum response. Okay, just their responses are different because the size are different. Okay, now if we further increase the filter size, you can see now the sunflowers even closer to the camera will give maximum response. Okay, and we can further increase the filter size. Okay, and the larger sunflowers, will give maximum response. And we can increase it to 15. And this is a very large filter. And these flowers will give maximum response. And further 17. This is the highest response. Okay. Anyway, so when we do blob detection, we need to apply a set of filters with varying sizes, small filter, the smallest filter, and maybe slightly larger filter, medium filter, large filter, the largest filter. Okay, we apply a pile of filters of varying sizes, and you can see the same image. For the same image, their responses are different to different filters of different sizes. Okay, so applying different filters allow us to identify blobs of varying sizes. Okay, now we need to take a look at all those response map and determine the interest points, determine the local maxima. And the local maximas are we only need to look at 3 maps. We only need to look at 3 maps because if the current we only need to look at 3 response map because if the current pixel is the highest, it will achieve maxima here. And this response. And for the filter, for the smaller filter or the larger filter, their response will be lower than its current response. So it's enough to look at 3 response map. Okay, similarly for this filter, it's also enough to look at 3 response map. And for this one, three response map. Well, so the idea is to examine 3 response map, and if the current pixel is larger than its 8 neighboring pixel, and it's also larger than the 9 pixels, the 9 pixels above it, and the 9 pixels below it. I mean, when I say pixel, I mean the the response map. Okay, so how can we identify key points or interest points? We need to apply a series of filters and we get those response maps. Okay, for example, we have 5 maps. We have 5 maps. We need to combine the information of the 5 maps to identify interest points. Okay, now we have 5 maps and we can just slide a cube. This is a cube. Each cube, for each plane, it has 9 pixels. Okay, we can slide this cube across the 5 map. And if the current pixel, if this is the current pixel, if the current pixel is bigger than its neighboring 8 pixels and bigger than the above 9 pixels or the below 5 pixels, then this is the interest point. Because it's the maxima, the local maxima. Okay, this is the local maxima. Okay, so here are the results. You can see those circles. The circles identified over this sunflower image. And the circle, the size of the circle indicate the size of the blob. And that was from almost 3 decades ago. Automatic scale selection. And this is also the results of blob detection. You can see what is the center? The center of the circle. The center of the circle indicates the location of the interest points, key points, while the size of the circle indicate the scale of the key point, the scale of the blob. Okay? The scale of the blob. Let's watch this let's watch this video. Sleep detector.
The SIF detector was proposed by David Lowe and is very widely used in computer vision. And one of the things that it does is it uses a variety of tricks to make it both reliable and very efficient. So let's take a look at one of these tricks. It's an approximation to the n-log operator. So here you see a Gaussian, n sigma, and if you subtract the...
Well, previously we talked about LOG, Laplacian of Gaussian. Okay, here the DOG means difference of Gaussian. The red curve here, this red curve indicate the LOG function, while the blue curve indicate the Laplacian of Gaussian. The blue curve is our log function. Well, dog means difference of Gaussian. Difference of Gaussian is used to approximate. Difference of Gaussian is used to approximate the Laplacian of Gaussian, which is to use the red curve, the red one, to approximate the blue one. Okay. So the purpose is to speed up, to accelerate computation, because it's easier to compute difference of Gaussian than log.
This Gaussian from another Gaussian with S sigma. That, it turns out, is a pretty good approximation to the n log operator with sigma, the same sigma here. So
N log operator, this is the Laplacian of Gaussian.
this is your normalized Laplacian of Gaussian operator. You get essentially very close to this, just scaled by s minus 1, but very close to this operator by simply subtracting these two Gaussians. So here you see the red curve is the difference of these two Gaussians for some s that's chosen. And the blue curve is the Laplacian of Gaussian, pretty close. So what that means is that the difference of Gaussian is just a scaled version of the normalized Laplacian of Gaussian. It's very useful because now, rather than computing the normalized Laplacian of Gaussian, you can simply take your stack of images, which is just the original image smoothed with different sigmas, take any two consecutive images and find the difference between them. You actually get the result you would have gotten if you had applied the normalized Laplacian of Gaussian to the first of these images. Very convenient. So now let's see how SIFT is implemented. Here's an image. The first thing you're going to do is create a stack of images where...
Well, previously we apply log to this image, and then we get different response map. But now we apply Gaussian to this image because we are going to approximate log with dog.
You're applying smoothing with sigma, s squared sigma, all the way to s to the power of k sigma. So that's your scale space right here. And now, in order to find the normalized Laplacian of Gaussian, which is what we're looking for, using the trick that I just mentioned in the previous slide that approximates it using the difference of Gaussian, you're simply going to find the difference between these two images. You get the normalized Laplacian of Gaussian right here, and you keep doing that to all pairs of consecutive images, and you get the stack you're looking for.
Okay, so previously we obtained this stack of image by applying log filter with different sigma. But this is slow. This is slow. Now we approximate this by applying Gaussian of different sigma, Gaussian function of different sigma, and we obtain this pile of images, this stack of images. And then their subtraction will give log, approximation of log. Okay, now this is the response map.
So this stack right here corresponds to the normalized Laplacian of Gaussian of the image computed at many different scales. So now we need to find extrema in the stack of images.
Okay, now we have the response maps. We need to find the key points. We need to locate the key points or the pixel, the location of the key points. And we do this by finding the extrema. Notice, extrema. So it could be maxima or minima. Okay? Extrema it could be the maxima, because if it's a dark blob, then it's maxima. If it's a light or white blob, then it's minima.
And we do that by using, say, for instance, you can do this in many different ways. You can use a small window.
So we do this by using a 3 by 3 by 3 grid. This, okay? It's like we slide this grid. We examine the grid across the stack of image, and we see whether the orange point. We see whether the orange point is the extrema among the 27 yellow points.
Window, maybe a 3 by 3 by 3 window, a cube, a grid, and you're going to move this grid around, and at each point you're going to say a small window, maybe a 3 by 3 by 3 window, a cube, a grid, and you're going to move this grid around, and at each point you're going to say, is this an extremum? This is the largest value in the window, and is it substantially larger than all the neighbors? If it is, you can declare it as an extremum. So this also.
So that's how we identify the interest points. We slide this cube. We slide this cube across the pile of image, and we see whether the center of the cube
back to the non
is extrema. If it is, then it is an interest point.
Maximal suppression.
If it is, it's the center of a blob. Some type of blob.
Algorithm we use for corner detection. There's many ways to find peaks in both 2D and 3D.
So this is to find peaks in 3D. Okay, we find the extrema in 3D by sliding this grid, this cube across the pile of response maps.
In this case, we're doing it in 3D. Once you do that, you end up with these interest points. These are your basically candidates for SIFT features.
Okay, now you see the red points. The red points indicate the interest points. For example, when you slide this, across the pile of image, and the extrema points could appear. It could appear at this pile. It could appear at this image, at this response map. It could also appear on this response map. Okay, it could the maximum point, because the size of the blob size could be are different. Okay, so the interest point may appear. The extrema can appear on each on different response maps
at many different scales. And of course, there may be too many.
You know, if it appears at this on this response map, then the scale of the blob correspond to the scale of this sigma. Okay. If it appear on this response map, then for all these interest points, their scale correspond to this sigma. Okay, because different response map is obtained from different sigma.
Many of these because you haven't really cleaned things up. So what you can do is use some kind of a thresholding scheme to then just preserve the prominent, the really strong extremas. That's after removing all the weak ones.
So we can apply some thresholding and to preserve the strong extrema.
And now you have your result. You basically have your SIFT interest points. So what do these look like with respect to the image we started off with?
Okay, now let's take a break. We will continue after break. Okay, let's take a break. right. Let's continue to explain SIFT detector. So I would like to mention that we use, this is the Laplacian of Gaussian. Okay, so this is the second order derivative with respect to Gaussian. And this is the second order y derivative with respect to the Gaussian function. Okay, so this is the LOG function represented by the blue curve. Well, the computation of LOG filter, the computation of this is expensive. So that's why we use DOG, difference of Gaussian, to approximate the blue curve. So that is to say, the blue curve can be approximated by the difference of two Gaussian functions, the two Gaussians with different sigma. For example, the k here, it could be 2. Okay, we have 2 sigma, or it could be 3. Anyway, it depends on you need to find a proper k to approximate the blue curve.
Welcome to another 341 sample video. This one is looking at what happens if you blur an image with a Gaussian kernel and then you blur the same image with a Gaussian kernel of a different size and then take one away from the other. So what I've got here is it's a black and white video feed from the back of some boring meeting or other, and it's actually blurred with a very small Gaussian kernel. And then what I do is I take exactly the same feed and you blur it with a bigger kernel, basically make it more blurry, and you end up with two versions of the same image but with different levels of detail in them. Where it becomes interesting is where you say, right, we're going to take one of these away from the other. So you take an image that's blurred with, say, a kernel of 3, and then you subtract from that an image that's blurred with, say, a kernel of 5. And what you get there is you get quite a good highlight of all of the fine detail in the scene. So you can see the twigs in the trees behind, and you can see bits of hair and so on. And the fine details, the twig, quite an image that's blurred with, say, a kernel of 5.
So this is the result of DOG. So if you subtract this from this, because these two images are blurred with Gaussian using different sigma. Okay, so if you subtract one from another, subtracting one from the other, you will give details at different scales. Well, using different sigma.
And what you get there is you get quite a good highlight of all of the fine detail in the scene. So you can see the twigs in the trees behind, and you can see bits of hair and so on. And the fine details exaggerated. When you make the kernels bigger, what happens is the fine detail disappears, but the broad brush detail is kept. And this technique is key to a lot of feature detectors, particularly those that work at different scales, like David Lowe's SIFT. By using Gaussian blurs and subtractions, difference of Gaussians at different scales, you get to highlight different parts of the difference of Gaussians. A good highlight of all
so look at this. Okay.
Kernel of 5. And what you get there.
And this is when you use, this is DOG, when the sigma is small. You can observe there are many fine details. But if you increase sigma,
is you get quite a good highlight of all of the fine detail in the scene. So you can see the twigs in the trees behind, and you can see bits of hair and so on. And the fine details exaggerated.
that's what happens when you enlarge, when you increase sigma. increase the kernel size. And that's the result of DOG when you increase
When
sigma.
you make the kernels bigger, what happens is the fine detail disappears, but the broad brush detail is kept. And this technique is key to a lot of feature detectors, particularly those that work at different scales, like David Lowe's SIFT. By using Gaussian blurs and subtractions, difference of Gaussians at different scales, you get to highlight different parts of the image and different types of feature.
That's why we apply DOG with different sigma. And DOG is applied by subtracting so you don't need to care for this. Okay, let's do not consider this. Let's only consider this part. Considering this part, we apply Gaussian kernel with different sigma to the image. Okay, and then we obtain a stack of blurred image. Okay, this probably this is the result of small Gaussian, and this is bigger Gaussian. Okay, so we obtain those smoothed image or blurred image, and then we obtain DOG by subtracting, for example, this from this. Okay, so say we have 5 blurred image, and then we subtract the adjacent images, and this will lead to 4 images, 4 response map, 4 DOGs. Okay, so this will lead to 4, you can see the details at different scale, the fine details, the brush details, as in the previous video. Okay, we have this DOG maps. Okay, and then we can perform detection on the DOG map because the DOG is just the approximation of LOG. Okay, and what about this? What about this? This is the implementation detail in the downsampling is the implementation detail in the SIFT detector, and you don't need to consider this. Okay. Okay, so you can see DOG is obtained by subtracting one blurred image from another blurred image, and this one K sigma indicate that it has bigger sigma, it has larger sigma. Okay. Okay. As you can see, when we apply different sigma, this is the result. When you apply different sigma, the image becomes more blurred. And now if you subtract this one from this one, and this one from this one, then you get a stack of DOG. Okay? Then we can identify the key point by moving a cube, by looking at the grid 3 by 3, the 3D cube. If the current point is key point, the key point is such a point that it achieves maximum response in the 3D cube. Maximum or minimum response in the 3D cube. Okay, so that's the SIFT detector, and we just explained how to do detection. And let's take a look at some results.
Right. Let's start with this one right here at this scale, the highest scale. Well,
Okay, so remember the key points identified at different scale, it comes with it comes with the key points I identify at a different layer or different map. It comes with the scale of the corresponding scale of such this the map. Okay, so this key point will have the scale same as this layer, because this layer is obtained by, by applying the Gaussian of the larger scale, DOG of the larger scale. Okay, and similarly, key points identified on the bottom layer will have the smallest scale.
Position right here corresponds to the position right here. That's where you have a blob, and the size of the blob is proportional to the scale at which you are. So you have a fairly large blob right here. And this feature right here appears here. This one appears here and has a smaller characteristic scale. Therefore, it's a smaller blob, and so on. So if you wanted to visualize all the interest points that were computed in this case, they look something like this. There's a lot of interest points that have been extracted. And of course, you can use thresholds, etc., to reduce the number and only look for really strong interest points. But this just tells you that even for an image like this, you can get a lot of features from the image, SIFT interest points. Here are some other examples. So here's an object, and you see every circle here is a SIFT interest point. And I just want you to note that not all of these are obviously blobs. We're looking at things that are blob-like, which have some interesting appearances within them. Here's another example, and yet another example. So we know how to find the interest points. We know their locations, we know their scales. So let's talk about scale invariance, because when you match these things ultimately, you want to remove differences in scale. So here is an example where you have an object and then a close-up of the object. You end up finding a SIFT feature here and here, which corresponds to the same appearance right here, but there are different scales. And since there are different scales, really what that means is that the n-log operator would have peaked at different points, different scales, different sigmas right here. This one peaks right here at a low sigma, and this one peaks at this one peaks right here at different points. Really what that means is that
the n-log means the LOG filter, LOG function. So the LOG function, gives the, for this image, the maximum response achieves at a smaller scale. The LOG function picks, because the image content, the two image, they have similar image content, but their scales are different. That's why when you apply LOG, they will pick at different scales.
That the n-log operator would have peaked at different points, different scales, different sigmas right here. This one peaks right here at a low sigma, and this one peaks at a much higher sigma. But because you know these sigmas, you can then normalize for this, meaning to say that you can adjust the scale of one to match the other. So in other words, all I'm trying to say here is that you can remove the effect of scale once you have detected one of these interest points. The other thing we need to worry about is orientation or rotation. So we need to remove the effect of orientation as well. For that, what we do is that imagine that this is, after the scale has been removed, this happens to be the area that the blob occupies. You can essentially place a grid in there. And for every pixel in the grid, you're going to compute the gradient. You're going to apply the gradient operator, which...
So these arrows, all these small arrows, they represent, for example, this arrow represents the image gradient. You know, image gradient, it contains, well, this is a vector, okay? So this vector represents, well, because it's a vector, so it includes x gradient, x derivative, and y derivative, okay? So this arrow, the direction or orientation of this arrow is computed using the arctangent of x derivative and y derivative. And so the magnitude, the length of this arrow is also computed by taking the square root of x derivative and y, the square root of x, the square of x derivative and the square of y derivative. Okay, so that is to say, for every pixel within this blue circle, for every pixel within this blue circle, we can compute its gradient vector. Okay, we can compute this gradient vector. Right? For every pixel, we can compute its x derivative and y derivative, and then we can compute the gradient magnitude and the orientation. Okay?
Which gives you the magnitude and the orientation of the edge at that pixel. And we're going to completely ignore the magnitude and only look at the orientation, the direction theta. And the reason we do that is the magnitude.
So now, so this is the y derivative, this is x derivative. Okay. And theta represents the orientation, the direction of the gradient. Okay, it's computed by the arctangent of this. Okay. So now, one approach is to disregard the gradient magnitude, but only look at the gradient direction.
Responds to or is affected by the lighting, the orientation, the direction, and magnitude and the orientation of the edge at that pixel. And we're going to completely ignore the magnitude and only look at the orientation, the direction theta. And the reason we do that is the magnitude, as you know, responds to or is affected by the lighting conditions, the gain of the camera, and so on and so forth. We want to make ourselves somewhat insensitive to those effects, and so we only look at the direction of the gradient.
Okay, so if we want to make your descriptor robust or your detector robust to lightning condition, for example, if for under dark condition, the gradients may have lower magnitude. Because so the magnitude of the gradient can be easily affected by the lightning condition. So if we want our detection to be robust to the lightning changes or illumination, variations in illumination, so we don't look at the gradient magnitude.
And now what we're going to do is create a histogram where on the x-axis you see different.
Okay, so now there are only 8 directions. That is, we can approximate, you know, these are like 8 angle directions, standard directions. Okay, and then we can approximate, we can round up. For example, for this gradient, it could be rounded to this one. Okay, and for this direction, for this gradient direction, it could be rounded to this one or this one, or this one. Okay, depends. So we're gonna make a histogram with 8 standard gradient directions. And then we're gonna run this, all these gradients with this.
Different directions for the gradients. And here you see the bars correspond to the number of pixels in here in your feature within this region which have that particular direction, edge direction. And you see that you get a peak right here. And that peak is what we'll call the principal orientation.
So the largest peak is the principal orientation. And this one is considered as the dominating direction of the dominating direction or the orientation of this image patch
of your feature. And so what this allows you to do is that when you're given two images like this, of course we're looking at the same feature here and here, it's the same interest point. This is the scale we're talking about, the size of it. You can compute the principal orientation in each case, and then you can undo the rotation of one to match the other case, and then.
So in this case, we can identify for the dominating or the principal orientation. Okay, the principal orientation, and then we can make the two image patches or the two features. We can make their, for example, let's rotate the patch according to its dominating or principal orientation. Okay, so we can all rotate them such that the dominating or the principal orientation points to 12 o'clock. Okay, can make them all points to 12 o'clock.
Two images like this. Of course, we're looking at the same feature here and here. It's the same interest point. This is the scale we're talking about, the size of it. You can compute the principal orientation in each case, and then you can undo the rotation of one.
We can undo the rotation by making their principal orientation points to 12 o'clock, making them to the canonical position.
So what I've described thus far is the fact that not only can you find these SIFT interest points, but in each case you can also, during matching, undo the effect of both scale and rotation. But what we haven't yet discussed is, what do we match on the basis of? What is the signature that we want to use to match two features? And that's what we're going to talk about next.
Teenagers are building businesses with AI while
Okay. So that's how SIFT do detection. How SIFT does identify the interest points. So we have all covered. We have covered this part. Now let's do a quick review. How do we look for extrema of DOG? Maxima of the DOG indicates dark point on a white or bright background. Minima of DOG indicates bright points or bright blobs on a dark background. Why do we look for extrema in a spatial as well as in scale sense? This is equivalent to say, why do we look for extrema in a stack of responses? And we have explained that because we want to identify the key points of varying scale, and these help us to pick the right scale. it helps us automatically identify the appropriate scale associated with the key point. Okay, for example, this is an illustration of SIF detection. Initially, we have the SIF detector have identified this many key points, but clearly, these key points that they are not important because they lie in some low contrast area. So we can remove this unlikely this key point this unnecessary or redundant key points. Okay, and then we obtain this, and we do not. So previously, these are the key points in the flat region. Remember, flat region that in the background. We don't want them. But we also do not want those key points on edges. Okay. So previously we have removed the key points within the flat region. Now let's remove some high contrast key points on the edges. We do not want the key points on the edges. So for example, this one. Okay, you can see those key points on the edges, and also this one. Okay, these are unlikely to be useful features, so we remove them. Okay, and finally, this is the identify. Those are the key points identified, and then we identify the principal orientation, and just as described in the video, we compute the gradient magnitudes and orientations. Well, please know that you may have different design choices. So in the video, they say the professor introduced that we may not use gradient magnitude. Okay, because gradient magnitudes may be affected by the illumination or changes. However, if you want to take gradient magnitude into consideration, you can also do it. You can also consider gradient magnitude when you make the histogram. When you construct the histogram map, the counts can be weighted by the gradient magnitude, or it's a different design choices. Okay, so the key point is to find the dominating orientation. The dominating orientation. This allows us to rotate the image patches. The dominating. Okay, this is the dominating. For example, this is a dominating gradient direction, and then we can, with the dominating orientation, if we know this, we can rotate them to a canonical position such that the dominating direction points to 12 o'clock. Then we can match them. Okay. And finally, we need some descriptor to describe the key points. And actually, this is our descriptor, the histogram. The histogram is the descriptor for the image feature. Okay. For example, now we have two image patches, and And this represents the scale identified. Okay, the scale identified. So first of all, let's look at the same image. These are the same image, but taken from different viewpoints. So they do not look exactly the same. All right. Now we have two features identified, two different features, two key points identified on the two images respectively. Okay. And we know their scales. The window size, the scale. When we identify the key points, we also identify their scale. Okay. When we identify the key point, we also identify their scale. This allows us to, because we know the scale, this allows us to remove their scale difference. Okay, for example, we can all rotate, we can all enlarge the image feature, the image patch to the same scale. Okay, so for example, the scale is 1.5, the sigma is 1.5, and this is 2. Because we know their scale difference, we can scale them. We can scale the window size to make their to make them have same size. And further, because since we have computed the histogram, we have identified the principal orientation or the dominating orientation. Then we can rotate the image to its canonical orientation. We can rotate the image. So, for example, for this image, its principal direction. The principal direction points to this direction. Okay. And for this one, the principal direction is this. Okay. Now, to align them, we can rotate this image such that its principal direction points to 12 o'clock. And similarly, this one, we can rotate this one such that its principal direction also points to 12 o'clock. So we can align them. Okay. Now you can see after scaling and the rotation, the two image patches they look very similar. Not exactly the same, but very similar. And let's take a look at their features. Let's take a look at the features. The features, well, within each cell is the, the histogram, a smaller histogram of the gradients. Okay, and as you can see, so they are not exactly the same because the two histograms are different, slightly different, but they are very similar. And this is the feature description for this patch. And this is the feature descriptor for this patch. Okay, they are already very similar. So when we do the matching, this feature will be matched with this feature. Okay, you can see their representations are very similar. Okay. So the descriptor is actually for each image patch, we divide them into 4 by 4 cell. and that's 16 cell. And for each sub patch, we construct a histogram. And we construct a histogram, and this histogram is something like this, and it has 8 directions. So each cell, within each cell, there are 8 directions. That's a number, okay? And we have 16 cells, and this will give us 128 dimension, 128 number. For each cell, there are a numbers like this, okay? So this is a histogram, a direction. With each direction, for each direction, there's a number indicating the count for each direction, okay? So for each cell, we need a numbers to represent each cell, and we have 16 cells, and this will give us 128 numbers. Okay, so this is the representation for this cell. The final descriptor is the concatenation of all histograms. (128) values. We have 4x4 descriptor. We have 16 cell. And each cell has each cell has a histogram. Each cell has 8 directions. Okay, so that's the SIFT descriptor. See, they are 16 cells for each cell. Within each cell, 8 directions. Okay, so that's the SIFT descriptor. But you can also use other choices. I mean, not necessarily 128. It depends
Hi, I'm
on.
Park Jae-hoon. Join Kinder Bueno K-pop experience and Santa Wins Trip to Seoul.
自信就係素顏依然晶瑩剔透 ，SK-II 神仙水 ，Pitera 3大功效。我嘅自信就係素顏依然晶瑩剔透 ，SK-II。
So, for example,
So
in
in
this video, I mean, you will see a slightly different SIFT descriptor.
We know how to find SIFT features in an image. We also know the size of the image. We know how to undo the effects of scale and orientation or rotation. What we need now is some kind of a signature that you can compute from a SIFT feature so you can match it with other features. So let's talk about how we do that. So imagine that this is an image that's given to you. You apply your SIFT operator, and then you end up getting these SIFT features. And this happens to be one of them. Let's focus on this one. Well, we know how to undo the effect of rotation by computing the principal orientation. We also know how to undo SIFT features.
So this is the dominating principal orientation. Okay, and you see we can just rotate the image or the image patch according to the dominating orientation. Rotate them such that it points to the standard direction, the 12 o'clock.
We know how to undo the effect of rotation by computing the principal orientation. We also know how to undo or normalize for the scale itself. So we can now take the content that's sitting in here and place it on a grid of some size, some standard size right here. That's this grid you're looking at. We also know that we can compute the gradient at each pixel in terms of magnitude and orientation. But what we're going to do, as we did before with the principal orientation, we're going to ignore the magnitude because that's sensitive to.
So So here, one approach is to ignore the magnitude, but you can also consider the magnitude. You can also include the magnitude information when you do the counting, when you count the histogram. But of course, this will lead to slightly different results.
The lighting and other effects. We'll just preserve the orientation of each edge in here. Okay, so now we're going to do the following. We take the first quadrant here, this quadrant, and we're going to compute an gradient orientation histogram. That's this. So these are all the different directions, and these are the number of pixels that have each of those directions. That's a histogram. And then we're going to take the next quadrant, this one, and then compute another histogram, and the third quadrant, and finally the fourth quadrant. And you're simply concatenating these orientation histograms together to create a long histogram, one histogram right here. Now remember that this histogram is normalized in the sense that it is invariant to rotation. We already have undone the effect of orientation or rotation. We have undone the effect of scaling. And by ignoring the magnitude of the gradient, we are also less sensitive to brightness. So this is something that we can directly use as a descriptor, a signature for matching two SIFT features.
So here, the descriptor only contains 4 cells. Okay, so previously we used 16 cells. Well, this is, that's just different design choices.
So how do we compare two SIFT descriptors? That's very easy. We can
you can use different distance function between the feature. The feature is just this is just a vector. This vector here, this is a 32-dimensional vector. 32-dimensional factor. Of course, you can compute the distance between such two vectors to identify whether they are the same feature, whether they are similar or not. Okay, we're going to skip this. These are just different distance functions.
SIFT detector works with images of objects. First, we're going to take a look at scale invariance. So these are images of the same object, but different scales, different magnifications. And each one of these lines that you see here corresponds to a successful match. So this is a little bit hard to see because you have lots of features and lots of matches, but you may want to just freeze the video right now and take a look at these matches.
Now let's take a look. So this feature match to this one, and this one match to well, I can see another small. That just too small. Okay. Anyway, the lines indicate the matches, corresponding matches between this object and this object.
You'll find there's a lot of very good matches here. Here's another example of another object, also plenty of matches. And given that you have so many matches, you should be able to then use these matches to recognize the object, as you can imagine. And now let's take a look at rotation invariance, an object and a rotated version of the same object. Once again, you can see a lot of good matches between these two images. A little bit more rotation. This was about 45 degrees. This is 90 degrees. And in this case, it's upside down, and you still manage to get lots of.
So even in the case of upside down, the two books, upside down, it can also successfully establish the very good matches.
Good matches. And here comes the big one, which is robustness to clutter. If you remember, we said that occlusion is one of the really hard problems in vision in general, but particularly
occlusion. Okay, so the upper half of this book is occluded by this.
Particularly object recognition. And so in this case, you have this object, and here the object is partially occluded. But whatever features were recoverable here from this object, you're able to find them in this object right here. And it doesn't have any mismatches with other objects. So that's really important. So you're recognizing the object in part, and that's all you can do when you have occlusion, and that's good enough.
So when we have occlusion, so we do not see the full object, but we can still match this object with the same object with if even though we can only see part of it, because it can identify same feature points in another image.
Enough for actually finding the object. Here's another example. This object is at a completely different scale, also partially obstructed, but quite a few good matches. And here is an even more challenging case where you have this object right here, partially visible here, and you can see that this is the orientation of the object that we were able to recover, and the scale as well. Now let's take a look at some other applications of the SIFT detector. Here is one which is very popular, which is stitching images together to create a larger image or a panorama. We're going to devote an entire lecture to this, and that's actually the next lecture. However, let's take a look at a simple case here. You have two images, and what you do is you first find SIFT features in both the images. And then you use the descriptors to match features, and you see that these ones match right here. And based on these matching features or correspondences of pairs of features, you're going to then essentially take one image and warp it and align it with the other image. This process of warping requires a geometric transformation.
So we do not introduce the warping. We do not introduce the warping process. Okay, we only introduce how to do matching, how to identify the key points and do matching.
We're going to talk about it at great length in the next lecture. But for our purposes here, imagine that such a transformation is possible. You warp them, and then you overlay them, and you get an image that looks something like this, a larger image. We'll also discuss in the next lecture how we remove these seams and make it a completely seamless panorama. The same thing can be done to construct collages. So here you have a large collection of images. You simply apply SIFT to each one of these, and then you match features among these different images, and you can bring these images together to create a single collage with a much wider field of view.
So this is quite amazing. We have this,
and you can
we have this many, like a dozen, more than 20 images.
Bring these images in
and we can just create a collage of this 20 or 30 images to create a large
together
view
to create a single collage with a much wider field of view. So we've seen that the SIFT detector and descriptor can be used to solve a variety of visual matching problems, and we showed how it can be used for recognition as well. So does that mean that the general problem of recognition of three-dimensional objects can also be solved using the SIFT detector? Not really. So the kinds of objects we've been looking at thus far are more like this. They're planar objects.
So SIFT is mainly applied for 2D object matching.
Perhaps with some complex appearance on them, but they are planar objects which are moving around on a plane. They may be rotated, they may be scaled in terms of magnification, perhaps even some occlusion and differences in lighting. But when it comes to 3D objects, things start getting more complex. So for instance, you looked at this object right here. If you look at it from this viewpoint and then from this viewpoint, the local appearances of these different features are going to be very different. So if you applied SIFT to two images of such a 3D object seen from different viewpoints, you will indeed get lots of features, but the descriptors are not going to really match. At some point, SIFT is going to fall apart. So let's take a look at when that happens. So here you have two images that are taken from roughly the same viewpoint. And as expected, you get lots of matches. Each one of these lines, once again, is a successful match. Now imagine an image taken from some angle and another image taken from roughly 30 degrees away. So you get these two images. And all of a sudden you see that there is a sudden drop, a dramatic drop in the number of matches between these two images. And if you keep going, as you would expect, here you have a 90-degree change in viewpoint. You hardly get any matches at this point. So all this to say that SIFT is reliable only for small changes in viewpoint.
Okay, it's only robust to small changes in viewpoint. Of course, that's quite natural. If you take photos, image were taken under quite large different viewpoints. Hardly, their appearance are totally different.
But that said, it still is an extremely useful and widely used detector in computer vision.
Okay, now let's summarize. SIFT detector. David Low SIFT detector. Actually, the very early idea appears in the 90s, the late 90s of the last century. Okay, and as we have seen, SIFT is robust to scale and orientation, and it can handle changes in small viewpoint change, 30 degree up to 60. Well, small viewpoint change, and it can handle changes in illumination. It can handle changes in illumination, perhaps which is achieved by, if we only consider the orientation of the gradients instead of the magnitudes, which can make the SIFT detector robust to illumination. And it's very fast. Okay, so it's partially invariant to image viewpoint. This is quite natural, and it's robust to occlusion or clutter, and invariant to illumination changes. Because when we make the histogram map, we may ignore the gradient magnitude information, which makes it robust to illumination changes. Okay, so that's some examples showing how SIFT detector can be applied to recognize objects and scenes under different scale, viewpoints, lightening condition, and occlusion. And here are the links to the two videos we have watched during class, and you can also watch it offline, which is very helpful. Okay. The SIFT descriptor. Now we are going to apply SIFT detector and the descriptor to do our lab 2 assignment, image stitching. Okay, let's take a 5 minutes break.
明白。
Hello everyone. This is the lab 2. Okay, today we will see the key points detection and matching. As you have learned from this class, I will introduce how to achieve the shift in OpenCV by using the OpenCV packages. The first step is install the OpenCV. The OpenCV library is a powerful library designed for computer vision process. This library can be used to across different platforms and is free available under open source IPAC license. It is written by using the C language, but it also provides a Python interface. So if you use a Windows computer, you can just open the command prompt and then type piping style OpenCV Python, and you can finish. Also, if you're using a Mac or Linux computer, you can just following this step by step to install your OpenCV packages. Okay, let's see how to read, save, and show images by using the OpenCV. Actually, in the lab 1, in our provided code, we have using the cv2.ImageRead function. This is also using this is also provided by the OpenCV. You can just look the code and try by yourself. After you using the CV2 to read image, and you can using the NumPy to process the image. And also the save images can just using the CV2 the image write functions. It is very easy. You can try by yourself. And the show images is also very simple. Just using the built-in functions such as the cv2.ImageShow. Also, you can using the wait key to close the images. Okay. There are also some utilities such as write and show, destroy all windows. Destroy all windows is using to close the images. Also, you can close the image by yourself. Okay, let's see a brief history of the key points detection. As you have learned from this class, there are several key points detection methods, such as the high-risk kernel detection, the shift, and the surf, and so on. Okay, let's see the high-risk kernel detection. This method was an early attempt to identify kernels in images, but the high-risk kernel detector is not reliable when the scale of an image changes. So in 2004, Lowe introduced a significant method called scale invariant feature transform. It's also named the shift to overcome these limitations. But the shift is a time-consuming method. So in 2006, Bay et al. Proposed a faster alternative called surf. As the name suggests, it is a speed-up version of shift. Also, in the 2011, there is another key point detection method named ORB, oriented fast and rotated brief. Unlike shift and surf, which requires payment for their uses due to the patent restrictions, patent is 专利. ORB is free from any such limitations. Okay. In summary, Harris is one of the earliest corner detection algorithm and contains the basic idea for corner detection. Shift is the first mature algorithm, although it is lower, and the Surf is a speeded up version of Shift. Orabi, on the other hand, is a free alternative of to both Shift and Surf. Okay, let's see the Shift. It is because the patent for Shift has expired, so it is free. As you have, because in the class you have learned the Shift very detailed, so in the lab tutorial, I will introduce how to use the Shift in OpenCV. It is very easy, just using the built-in function, you can achieve this. Okay, in this section, we are going to detect key points in two images via the classical Shift detector. Find the corresponding key points, calculate the transformation, and then align the two images. OpenCV has APIs for other key points detection algorithm. So once you have familiar with aligning images using Shift, you can try the other APIs by yourself. Okay, let's follow the instructions step by step. The first is detect key points and generate key points descriptors. And the second step is match the detected key points between the two images. And the last, you need to align the two images and stitch them together into one. Okay, here is an example of the two images. The first image is left of the whole image, and the second image is right of the whole image. And by using the Shift algorithm, we can stitch the two images into a big image, such as the third image. Okay, let's see how to use in the OpenCV to achieve this process. First, it is important to ensure that the image we are working with have a data type of NumPy unit 8. We can then process to convert them to grayscale, since all key point detector in the OpenCV can only handle 6 channel images. To process colored images, we have two options. Either convert them to grayscale or perform detection on each channel individually. As you have learned from the lab 1, you should need you may need to have learned how to change the color images to the grayscale images. So we just jump from this step, and the next we can detect key points in images and generate descriptors by using the built-in function Shift. First, you need to create a Shift object using the cv2.Shift create method, and then just using the Shift.detect and compute method. You can get the key points and the descriptors as the result. This function's input is the grayscale images, which named the image gray. And the mask you just using the num is okay. Okay. After using this built-in function, if n key points are detected, the return values will have the following structures. Key points is a list containing n cv2.keypoints objects. Each key point object has the following attributes. It includes the angle, PT, response, and size. The angle indicates the orientation of the descriptor, and the PT means the represents the location of key points in the form of a tuple, and the response is signifies the key points response, where a high value suggests a higher likelihood of being a key point, and the size denotes the scale of key points. Okay. You just know these attributes is okay because in your practice you don't need to know this very detail. Okay, you can print the objects and you can find the what it means. It's all numbers. The descriptors is also a array, NumPy array object of size n and 1 to 8 matrix. Each row stores an 1 to 8 dimensional descriptor for the corresponding key points. You can print the descriptors and you will find that the descriptor is a matrix. Okay, to draw the detected key points on images, we use the cv2.drawKeyPoints function. By passing the cv2.drawMatches flags, draw reads key points flag as a parameter. Using this is okay. This flags is just using these flags, you don't need to change it. The function will display not only the location but also the size and the orientations of the key points. So this is the results of the two original images, the two original left and the right part of the whole images. Okay, after you got the key points, you need to finish the second step, matching. Okay. Let's assume that we have detected key points in both image 1 and 2 and generate their descriptors using the following method. Okay, just using the CV, the shift dot detector and compute function is used to get the key points as we introduced in the first step, and the next step is to match key points between two images. This is done by finding key points pairs from the two images with similar descriptors. Okay, how to get the similar descriptors? We use the Euclidean distance. It is also named OG 里的距离. Assume we have two 1 to 8 dimensional key points descriptor UV. The distance is defined as the following formulation. Okay, the small distance value indicates that key points U and V looks similar. In the matching process, for each key points in image 1, we always match it with the most similar key points from image 2. You may fail to compute the Euclidean distance a little hard. Don't be worried. You can use the built-in function, such as the brute force method. The matching process can be performed using the cv2.bf method in OpenCV. This function's input is two images descriptor. Take this example. The query descriptor is descriptors 1 from the image 1, and the train descriptors is the descriptors 2 from the image 2. Okay. After using this function, the return value match is a list of cv2.dmatch objects, each with the following attributes. It includes the distance, query, and index and the tree index. Okay, you can print the attributes by yourself, and you will see it include the distance and the index from two descriptors. Other than the BF measure, you can also using other measures such as the flan based measure. Because BF measure will compute all key points in the it is because the BF measure will compute all features in the in two sets, so it is slow. To overcome this, as an alternative, fast library for approximate nearest neighbors, also named flan, is available. Flan is a faster version of BF measure. Its usage is similar to BF measure, but it offers improved speed. You can change the measure by yourself. The next step is using the Loess result test. In some cases, the matching result may contain a significant number of false matches. To mitigate this issue, we can employ the result test as described in Loess paper. In Loess result test, its key point from the first image is matched with a certain number of key points from the second image. If the two match distance are not sufficient different, the key points is eliminated and not utilized for the subsequent calculation. Just following this code, you will achieve the Loess result test by yourself. The next step is to select good matches. Distance measures goodness of the match. We only select the match with small distance and remove those with large distance. This step is also very easy. For example, we only take the best 100 matches, and we only we just need to shorten the match and take the best 100 matches using this method. After we got the best matches, we can draw the match. We can visualize all matching key points using the built-in function named draw matches. The draw matches input include the image 1 key points from image 1, image 2 key points from image 2, and the best images and the best matches. After using this built-in function, you will get this result. You can see the image 1's the two images matched key points will align where every matched key points will be related by a line, like the matched key points. The next step is to state the image 1 and image 2. This is the final list step. To do this, we first need to obtain the coordinates of all matched key points. Just using this method, it is very easy. To do this, first we need to do the perspective transform to ensure that both image 1 and image 2 are in the same coordinate system. we need to perform a perspective transform. This involves calculating a transformation matrix based on the corresponding key points between the two images, and then applying this transformation to image 2. Hereafter, we refer image 2 as a source image and the image 1 as a destination image. Calculate a perspective transform from source destination image just using the find homograph function. This is also a built-in function in OpenCV. You can just using this. Also, not all matched key points pairs are correct. Incorrect matches can result in an inaccurate transformation. To determine if a match is accurate or not, we can check if the pairs are sufficient close after transformation. So in the built-in function, we need to define the method. Just following the tutorial using the CV2.use using accurate method is okay, and it also needs another parameter, which means the runs. This is a threshold to determine the function. You can just set it to 3 pixels or 2 pixels. All these are okay. The return value slitters indicates the correctness of endpoints. If the slitters equals 1, means that source key points and the destination key points are considered a correct pair. So by using this formulation, we can get the final results. Also, we can using the CV2.raw perspective function to apply the transformation T to image 2. After using these functions to image 1 and image 2, we can go to the transform the image 1 or image 2. This is the function. You can see that the two images are transformed into the same coordinate. Additionally, we need to pad image 1 with the zeros to ensure that it has the same dimensions as the transformed image 2. Just using this function is okay. Okay, finally, we just need to stick the two images together. The final step is to combine or stick these images together by directly averaging them. We obtain the following results. Because the image 1 and the image 2 are divided by 2, so only the overlapped part is light and the other part are darker. To overcome this, we need to using the following steps to restore the dark parts. Okay, just following these codes, you will get the final results, and this is a smart average. Okay. This section is about how to stick two images, and in the next station, I will introduce how to stage in a video. This named panorama staging. Okay. this function is to process video, so we need to read a video from your computer. Just using the read video frames from the utils Python file, you will read you can read the video from your computer. In the case of a panorama, its dimensions are typically several times larger than those of radio frames. For the example video, we let the big H and W are four multiple the small h and the three multiple small w. By using this method, we can go to a large canvas. Okay, next we initialize our panorama by placing the first frame to the canvas. For this video, since vCore is scanned from its bottom right corner. Okay. This is the video. This is the video's example. The video is start from the right bottom corner. So we set the first frame to this place. Okay. By using this code, you can place the first frame to the right bottom place, and the next we align all frames to the initial panorama one by one, similar to what was done in the previous section. We also keep track of uncertainty variable to record the count for each pixel and a sum variable to record the sum. To reduce the computation, we can only state every 4 or 6 frames. Okay. This to-do part is your homework. You need to finish this by yourself. This is about how to state the frames from a video, and the next station is about video stabilization and stack denoising. Sometimes the images we capture may contain a significant amount of random noise, particularly in low light conditions. One of the most observed type of noise is known as the white noise, which is depicted in the images below, such as the noise images equals to the original images at the noise, the white noise. A noise image can be seen as a combination of both the original image and the noise components. One approach to reducing the noise is capturing multiple images or frames of the same scene and then combine them to obtain a clear image. Let's assume we have n images or frames captured for the same scene, and by averaging all the images together, the scene itself will be preserved while the noise will be smoothed. Because every noise is different. After the noise divided by n, it will be very small. So we can see that we only have, we have the original images. This is the basic idea of stack denoising. Ideally, if some images are perfect aligned, the final image will exhibit good performance. However, in reality, the multiple images are often captured from slightly different locations or perspectives. The video may also lack stability, resulting in blurred images when directly stacked. To address this issue, we need to perform 2 steps in this procedure. the first step is aligning the images, and then we need to average the aligned images to generate the final denoised image. If you don't want to using this algorithm, you can use the tripod, but it is very heavy, so it's not reliable. Okay, let's see the first example. It is the long exposures, which is suitable for capturing dark scenes. However, there are situations where long exposures alone may not be sufficient, particularly in extreme dark environment. In such cases, we can capture multiple images of the same scene and combine to obtain a clear image. Okay, you can find this example from the left to right. The first image is no long exposures. You can see it's very dark and you cannot see the object very clearly. And the second picture is the three long exposure, and the third image is stick 10 long exposure images without stabilization. It is very blurred, and after you using the stabilization algorithm, you will get very clearly images. This is the first images. Expect the long exposures. This denoising method can also be used in the deraining scene, because stick denoising can you can see these images as we introduce in the lab 1. As we introduced in the lab 1, in lab 2, you can also using another denoise method to do the deraining method, to do the deraining task. Because in the lab 1, we're using the median filter to do the deraining task, such as in these images. After we using the median filter, the image will be blurred. But using the stack denoising method, such as in the last images, the images will not be blurred. So the stack denoising overcomes this limitation by producing a clear ring-frame outcome. However, it requires multiple images as input. So, the following so the deraining method's inputs all usually be multiple images or video. And because a video include several frames, and you can using the frames to do the deraining task. Okay, let's see the lab tools assignment. As same as the lab 1, it also include 10 points with 2 bonus points. The first assignment you need to achieve is using the shift to do the image alignment. Because this lab tool allowed you to using the OpenCV packages, so it is easy to achieve this step by step, just following this tutorial, and you will find it's very easy to finish. And the second assignment is creating a panorama from a video. It is 4 points, but it's a little harder than the first task. You need to read the frames from the video. This code and the video I have uploaded in the Blackboard. You can just download and process this video by yourself. You need to read the video and using the panorama and creating a panorama by yourself. And the last is the bonus part. It is stabilizing rainy videos to create rain-free images. The third task involves stabilizing the video rainy the rainy video to create rain-free images by stacking all frames together. To complete this task, you need to follow the this step by using the and finish the derun Python file. Also, you need to save the final results and the intermediate results to a file. Okay, let's send the submission instruction. You need the deadline for this submission is in November 2023. You have 1 month time to finish the lab 2. Multiple submissions are allowed, but only the last submission will be graded. Okay. Okay, that's all. If you have any questions, you can tell me by using email or Teams